We have been looking at some elementary properties of thermodynamics, the laws of thermodynamics, the classical ideal gas and so on, and today we turn to a very important topic in the study of thermodynamics and statistical physics in general, namely the fact that substances undergo phase transitions, changes of state, for instance from solid to liquid or liquid to gas and gas to solid and so on and so forth. We would like to begin to understand how this happens, and the way to do this is to, as a preliminary, start with the idea of an ideal gas and then ask to what extent does it actually mimic a real substance and what is the basic difference between a real gas and an ideal gas. So let us go back to the ideal gas and notice that in the case of the equation of state was PV is RT for 1 mole of the substance, and this implied immediately that in thermal equilibrium, if you fix the pressure and the volume, the temperature is fixed. If you fix any two of these, the third one is fixed by this equation of state, and we can plot in the so called phase diagrams, we can plot for instance P as a function of T, and this is clear that if V is constant and you have a fixed amount of material, this is some kind of straight line. On the other hand, you could also plot P versus V here for a fixed value of the temperature and you get a rectangular hyperbola of this kind. You increase the temperature, you get a different hyperbola, etc. There is no way in which this substance, this gas, can actually condense to form a liquid. On the other hand, we know that in real life, when you take a gas and you increase the pressure on it and decrease the temperature, there comes a stage when the gas condenses into a liquid. So this ideal gas law is clearly inadequate to explain the fact that matter condenses at lower temperatures into the liquid and solid forms. Now how do we go about trying to fit that into our formalism? But the way to do this is to go back and ask, what did this gas law come from? Remember that it came from the fact that if you plotted the intermolecular potential V of R as a function of the distance, so imagine you had one molecule at the origin of coordinates and another molecule at distance r from it, then the real intermolecular potential for neutral molecules is typically of this form, as we have seen several times, namely below a certain distance the force is repulsive and after a certain distance there is a long range attraction. We even saw what the form of this potential would be like. It is like 1 over r to the 12 divergence here and 1 over r to the 6 decay to 0 on that side. The ideal gas on the other hand is based on the assumption that this interatomic potential, intermolecular potential, is essentially infinite at r equal to 0, hard spheres or hard points colliding elastically with each other, and there is no attractive force at all beyond that, no interaction of any kind. So it is not surprising that no matter how much you increase the pressure and decrease the temperature, this model will not display condensation into a liquid phase or any condensed phase. On the other hand, to rectify this was a major problem at the end of the 19th century. Van der Waals and several other people proposed modifications to the ideal gas equation of state, and the modifications proposed took into account the intermolecular potential. The one that became most famous that we use today as a sort of prototypical model of a non-ideal gas law is the following. It says instead of this intermolecular potential, let us approximate this by the following picture. Let us assume that below a certain distance there is an infinite hardcore repulsion and beyond a certain distance there is simply an attraction, a long range attraction. So this is an approximation, this graph is an approximation to this real life graph here, the real physical graph here. Even that correction suffices actually to produce some features of real gases, and this is what the van der Waals equation of state is. So this sort of approximation will lead to, after a lot of calculation, will lead to the equation that van der Waals actually wrote down empirically based on very simple considerations. On the other hand, to derive it from first principles using statistical mechanics and this intermolecular potential is a much harder task, but we know where the physics is in what van der Waals already wrote down, and his idea was the following. He said this implies that the pressure is actually equal to RT divided by V minus B, because he allowed for the fact that these two atoms have two molecules cannot get arbitrarily close to each other and sit on top of each other, but there is a certain excluded volume due to the finite size of the molecules. Well, today we do not call a finite size for the molecules because these are quantum mechanical objects and they are fuzzy objects in some sense, but what we would say is that there is a short range repulsive force between them which makes the cost and energy too high for them to actually get in closer than a certain minimum distance from each other. So that is taken into account by saying the actual available volume to the gas is less than the volume of the container V. So there is a subtraction here, and then there is the fact that they attract each other at long distances implies that if you put them all these molecules inside a container, it implies that due to the attraction they have for each other at long distances from each other, the actual average force on the walls of the container is reduced from what it would have been if this force had been absent. In other words, there is a subtraction to this which is of the form some constant over V squared. There is actually a very simple physical argument which tells you why it is 1 over V squared and not V cubed or 1 over V or any other power, but I do not want to get into that now. What we need to see is that this gas law, this is the van der Waals, the famous van der Waals equation of state with A and B certain positive constants, and this equation of state is what we would like to work with as a correction to, as an improvement upon the ideal gas equation of state. Well, the first thing we do is immediately plot what its isotherms look like, and instead of these isotherms you now get a new set of isotherms which is quite different in shape, and it is as follows. So we need a largish picture, so let us draw this properly. That is volume and that is pressure, and I am going to plot isotherms, in other words keep T fixed and ask what this graph looks like when I plot P versus V here. Now if you rationalize this, move this to the numerator, you see immediately that there is a cubic equation, cubic power, the third power of V appears. So the equation, the curve is not a very easy curve, not a simple curve, not a hyperbola or anything like that. On the other hand, if you look at very high temperatures and high enough pressures and volumes, then this correction is negligible and essentially you end up with P is RT over V, the ideal gas. So we kind of qualitatively expect that way out here these curves are going to be like the ideal gas approximately, but as you come down here, depending on the values of the parameters B and A, remember these are physical dimensions, the curve looks very different altogether, and there comes a stage where you have a curve with a little inflection point, and below that the curve starts developing a knee, and below that it develops a bigger knee, and so on. This is very sketchy, but one could try to fit curves of this kind to real gas equations and extract the values of the parameters A and B. When you do that, you do not get a curve which looks overall in this shape, but it does not look quite like this. For ease of convenience of drawing, I have drawn it very schematically. What really happens is that with actual values of A and B put in from real gas data, it turns out that the slope here on the left hand side is much greater than the slope here on this side by a factor of 1000 in typical cases. So it has serious physical implications which I will talk about in a minute, but you can see that qualitatively the graph has this shape. So below a certain temperature, so T greater than a certain critical temperature, this is the isotherm at T equal to Tc, the so called critical isotherm, and we will see what that means, and below that the curve has a minimum and a maximum. Mathematically what happens is above Tc, so here is an isotherm for T less than Tc, this is much less than Tc, and so on, and this curve here is T much greater than Tc, etc. Mathematically what happens is that there is an inflection point on the critical isotherm. Let me use that word here and then explain what it means. An inflection point where the slope vanishes, P is flat locally as a function of V, and the second derivative also vanishes, so the curvature is also 0 at this point. And below Tc, this inflection point resolves into a minimum and a maximum out here. So these two separate from each other and go further and further apart as the temperature is lowered further and further. What this means now is that this gas equation, this isotherm, this equation of state, the van der Waals equation of state, is doing a little more than what we had expected of it. It is actually telling us that at sufficiently low temperatures, and by low I mean lower than this value Tc, which by the way can be computed. So we can compute this point, this point has coordinates Vc, Pc, and it is of course at temperature Tc. We can compute this by solving 3 simultaneous equations. So solve for P, V and T from this equation delta P over delta V at T equal to 0. This says the slope is 0 on an isotherm, so constant temperature, differentiate this equation of state with respect to V, you get an algebraic equation, put that equal to 0, and then the curvature is also set equal to 0. So solve for this from d2P over dV2 at T equal to 0. You have 3 equations between 3 quantities P, V and T, and therefore if there is a solution it is a unique one, and indeed it turns out there is a unique solution. Solve for this P, V and T from this to obtain the constant values Vc, Tc and Pc in terms of A and B, and of course the gas constant R. So that is a simple exercise in algebra which I am not going to do to save some time, but in principle we are not concerned with it at the moment. There exists a characteristic Vc, a Pc and a Tc, functions of these parameters A, B and R, and uniquely determined such that above Tc, T greater than Tc, the isotherms do not have a kink like this or a minimum and a maximum and behave more or less like the ideal gas equation of state, but below it has got a feature that there is a minimum and then a maximum and down, and there is one wing of this curve which has got a very low slope, negative slope but very small in magnitude, another which is a negative slope but very high in magnitude. And what does that imply? And I have already mentioned this is about 1,000 times as big as that. What this implies is that the slope here has a physical meaning. And what is the meaning of the slope in this curve? Delta P over delta V at constant temperature has a physical meaning. This says this is very large. Now go back and ask yourself what the bulk modulus of the gas is, or the compressibility, which is the inverse of the bulk modulus. The isothermal compressibility isothermal because we are concerned with constant temperature processes, these are isotherms here, and let us give it a name K sub T, is defined. Definition: compressibility is the reciprocal of the bulk modulus is stress over volumetric strain. delta P over the volumetric strain. This is the inverse of it. So, this is equal to minus 1 over V delta V over delta P at constant temperature. So, it is the reciprocal, apart from this factor, it is the reciprocal of this slope here with a minus sign. Why minus sign? Because it is obvious that if you increase the pressure on a gas, the volume must decrease. So, this would become negative, and a minus sign here would give you a positive value for the compressibility. The compressibility cannot be negative. That is taken care of by ensuring that the slope of this slope here is always negative, and that indeed it is out here and out here, but it is not here, and we will come to that in a minute. So, this portion seems to be giving us some trouble, but you can immediately see that if the slope is very large in magnitude, then the reciprocal of that slope is very small. So, the compressibility is very small, it is very rigid. If the slope is very small, this slope, its reciprocal is very large in magnitude, and therefore you have a very compressible system. So, this portion is very compressible. This portion on the other hand is very incompressible. So, it suggests that since this is 1,000 times as incompressible as this, that perhaps this system is actually, this equation is describing not only a real gas, but also the corresponding liquid on this side, and indeed this is so. So, this is the liquid phase of the same substance, and this is the gas phase. So far so good. So, it is giving us a bonus. It is actually saying that when you include the long range attraction between molecules by means of the van der Waals equation, you are actually ensuring that below a certain temperature there is the possibility that the same equation of state describes both the gas phase and the liquid phase of the same substance here. So, this is actually giving us a handle on how to approach the problem of the change of phase from one phase to another. This is the very first preliminary step here, but we have to overcome a certain problem before that, which is the fact that in the region between the maximum and the minimum, the slope is positive. This slope is positive, but that is very unphysical. It says if you increase the volume, the pressure increases, or if you increase the pressure, the volume increases, whereas Le Chatelier's principle tells us that it should actually decrease for stability, it cannot increase, and this part of the isotherm cannot be correct, it is unphysical. Now let us see what other consequence it has. Let me draw another diagram, a simpler diagram, and look at just one of these isotherms. So, once again, here is V, here is P, and if this is your isotherm, then this part is the gas phase and this part is a liquid, describes a liquid, and this is at some temperature T less than Tc, some fixed temperature T less than Tc, then this portion of the curve is unphysical, it cannot happen. The model is wrong, the van der Waals equation of state cannot be completely correct, it is oversimplified certain things so that you end up with this unphysical portion of the isotherm. It has another consequence. If this were correct, it would have another consequence. It would have the consequence that as you increase the pressure in the gas phase, there should come a stage where the system condenses, and what would happen as you increased, keeping the temperature constant, is that it would jump here and then move up this isotherm. So if you took the gas phase and compressed it at constant temperature, you increase the pressure at this pressure it would become a liquid and thereafter remain a liquid as you increase the pressure further. On the other hand, if you started with the liquid and decrease the pressure, it would have to come down all the way here and then jump here to the gas phase and go on in this fashion. So this would mean that if you condense and liquefy and condense and evaporate, keeping the temperature constant, you end up with a hysteresis, you end up with responses or the transitions at different values of the pressure, and that does not happen in practice. So what really happens in practice is that if you took the gas phase and you increase the pressure, there comes a stage when it makes us change in this fashion and goes up, and when you decrease the pressure at precisely the same value of the pressure, it becomes a gas and goes down here. So this unphysical part of the isotherm together with the portion which is in the positive slopes and the correct slope here, these two portions are excised, are removed in real life, and the van der Waals equation of state has to be modified a little bit in order to take this into account. This construction was actually provided by Maxwell, and I am not going to get into that here, but you could ask at what point does this happen, when does this happen here, and the answer is it happens when this area is equal to that area. This is called the Maxwell tie line construction. This is called a tie line, and it is an equal area construction here for reasons which we will not get into here. So the real set of isotherms for real gases, for a gas and liquid system, is the following. You have got these isotherms which look like ideal gas equations, and then the critical isotherm, and below that you have this set of isotherms in this fashion. So that is what a real system looks like, and you could ask what happens if I took the system and suddenly brought it to this point here. Where would it be? What would it do? Well, it would phase separate then into a portion that is liquid and a portion that is gas. If you brought it here, it would phase separate in a specific manner using a rule called the lever rule, which tells you how much of the liquid and how much of the gas or saturated vapor would be in equilibrium with it. But this is an extra detail which we will not get into here, but the point I want to make is that this explains, or rather gives us a handle on how the liquid phase is attained. So there is actually the possibility that in the van der Waals equation of state you can, with a modification due to Maxwell, actually understand both the gas and the liquid phases. The gas phase has a very low rigidity, very high compressibility, and the liquid phase has very high degree of incompressibility, or it has high, its bulk modulus is very, very different from that of the gas here, which is highly compressible here. So much for the fact that real gas also allows for the possibility of condensation. The next thing we have to do is to ask what does this look like in a plane other than the PV plane. Suppose we did this in the PT plane, what would happen? And that brings me to the next topic, which is the change of state that materials undergo. So let us go on to the so called change of state. I put this in quotation marks. It should really be called phase transitions. And along with that is the phase diagram. I would like to emphasize before we get on to this that the technical way of saying this, the correct way of saying this is is a phase transition rather than change of state, because the word state is somewhat vague. Although it says in textbooks, elementary textbooks, that matter exists in 3 states, there is a liquid state, the gas state and the solid state. This is a little imprecise for various reasons, which some of which I will mention here. For instance, if you say a liquid is different from a solid because a liquid does not support shear. Under shear it flows, whereas a solid has a shear modulus and does not flow. Then I point out that depending on how rapidly you change the stress on the liquid, it may act like a solid. As we know, if you take a dive into a swimming pool and you land on your stomach and you land vertically down very rapidly, you can get hit as if you are hitting a solid object. So the liquid essentially behaves like a solid object here. On the other hand, even a very solid looking object like pitch or tar will, if you allow it to flow and you put a stress on it and allow it to flow, it will flow extremely slowly, maybe at the rate of a drop a year or a century even. Such an experiment is on, by the way, a famous experiment where drops of pitch, single drops fall every several decades later. So it flows like a liquid. On the other hand, it is in the liquid state, it is in the solid state, but it flows like a liquid. On the other hand, the liquid, the swimming pool example I gave, behaves like a solid depending on the strain rate that you apply on the system. Similarly, if you say a liquid flows whereas a solid does not flow, I take a crystal, I powder it, it becomes microcrystalline and then it becomes a powder and it pours exactly like a liquid. So here is a system which is apparently in the solid state but pours like a liquid, and there are liquids which behave like solids as far as stress response is concerned. So there is really no precise way of saying this, except to say that the word state is not very precise. You could have something in the solid phase, which is a thermodynamically well defined statement, and then in this phase you can have all kinds of physical states. You could have a state where it is granular, where it is microcrystalline, polycrystalline, single crystal and so on, or even amorphous. You could have, for instance, various kinds of intermediate states. When you take a solid and or a powder and you mix it with a liquid, you can have an emulsion, you can have a gel, you can have all kinds of objects of this kind which would all correspond to various physical states. But as far as the thermodynamic properties are concerned, the word phase has a very precise meaning. And here let us distinguish in the simplest instances between the gas phase, the liquid phase and the crystalline solid phase here. So if we restrict ourselves to that, then we can actually begin to make some precise statements, and this is what we will do next.